Welcome back. I'm glad you were very excited and eager to do more examples out of section 2.6. So suppose we have a rectangle. It has one corner in the first quadrant. Remember, whoops, previous slide. Remember that the quadrants are laid out like this: quadrant 1, quadrant 2, quadrant 3, quadrant 4. So one of the corners is in quadrant 1. It's on the graph of 16 minus x squared. Okay. Another corner is at the origin, another is on the positive y-axis, another is on the positive x-axis. So they haven't given us a lot of space. I just want to justify where this picture in the bottom right comes from. So I know one corner is here, one corner, so that's the corner that's at the origin. A corner is on the positive y-axis, a corner is on the positive x-axis. Notice this already tells me two sides of the rectangle, and here's a right angle. And in a rectangle, all angles must be right angles, which tells me the other sides have to do this. So the other corner has to be somewhere here in the first quadrant, and they're just telling us it's on this curve. So here's where this picture down here came from. We have 1, 2, 3 corners given to us, and we know the fourth has to belong somewhere on that curve. This really locks down where this corner and this corner can possibly be, because then this horizontal line coming through that corner of the rectangle and this vertical line going through that corner of the rectangle have to meet somewhere on that curve. So I can't just draw like any rectangle I want. If that corner isn't on this curve, that would be bad. So express the area as a function of x. What is the domain of this function, and for which value of x is the area the largest? Now this sounds like a really sort of hackneyed example. Why would I start this section by talking about real-world problems when so far I'm just talking about points on lines and areas of rectangles? The honest answer is, for real-world applications, the functions that we use are horrendously awful. Okay, so here, what function are we dealing with? Basically, we have a nice quadratic parabola that we have to play around with, and that's something we can do. The functions that are from real-world examples are much more complicated, and you need a lot of practice to get up to working with them. And if we just started throwing really terrible functions at you, students would complain. They'd say, I hate math, this is impossible. So we start off with something a little more straightforward, but then they complain this has no applications, this has got nothing to do with reality. So we're just trying to find the largest possible rectangle we can with a certain restriction that the corner has to be on this curve. That's really what this problem is about. Okay, so the one thing you have working for you is that whatever this point xy is, you know that y has to be 16 minus x squared. So try to express the area, find the domain, graph the function, and find where it's the largest. Okay, so I'll pause here and then we'll go through the solution. All right, moving on. So our rectangle, the area of a rectangle is just base times height. And if this point is at x comma 0, and this point is at 0 comma y, and this point is therefore at x comma y, we know that this width is x and this height is y, so the area is just base times height, x times y. But we also know that y is 16 minus x squared, so the area is x times 16 minus x squared, which we distribute to 16x minus x cubed. We have to be in the first quadrant, and that means x and y both have to be positive, but we're only asking domain, so forget y for the moment. X has to be positive. That's your domain. But it's a little more restricted than that, because we had to intersect this curve, which means x can't go beyond that root. Okay? And the curve was 16 minus x squared, so I want to find where that root is. So I'll set this equal to 0. This gives me x squared is equal to 16. X is plus or minus 4, but I'm in quadrant 1, which means x has to be positive, so x is 4. Okay. So x certainly can't be bigger than 4. Now if x were equal to 4, I'm going to have to erase this picture in a second, but if x were equal to 4, here's the parabola, what rectangle would I get? Well, one corner is here, one corner is here, but the other corner is here and the other corner is here. It's not actually a rectangle, it's just a line segment. So that's not a valid choice either. Okay. So x has to go, cannot go all the way up to 4. It also has to be positive. So overall, what's the domain? Yeah, I knew I was going to have to erase that. Overall, the domain is the interval from 0 to 4, not including either endpoints. So here's the graph of that function, 16x minus x cubed, with the domain restriction starting at 0 and going to 4. Using the maximum function, you can find that the maximum happens at x is about 2.31. Okay, next example. A word problem. Again, students like to say they hate word problems. They also like to say they want to learn applications, and you can't have it both ways. All right, suppose two flying cars at the same altitude. You know what? For the sake of making this simpler, I'm going to say their altitude is 0, and they're just cars, are driving at each other, okay? One is going south at a ground speed of 60 miles per hour and is 4 miles from the intersection. The other is going west at 80 miles an hour and is 3 miles away. Okay. Build a model that expresses the distance between the cars. Notice they're both moving with time. So the fundamental independent variable here is time. They're going to be at a particular place at a time, and I need to know what is the distance between their respective places. And then graph this and ask what's the closest they come and when does that happen. Okay, so I'll pause here. This one's trickier because you have to come up with something with no picture or function or anything given to you. But I'll pause here, do what you can, okay? One is flying due south at 60 miles per hour, 4 miles away from the intersection. Here's my hint. The point of the intersection may as well be the origin. You can make it wherever you want, but life is going to be simpler if you just say the potential point of intersection is the origin. All right. So here's their fanciful little picture. The red car is going south towards the origin, and it started 4 miles away. So at time 0, the car is here. The blue car at time 0 is here, and it's headed that way. Okay, and by arranging one of them to be coming down the y-axis and the other going left along the x-axis, we've guaranteed the origin is the potential point of intersection. Okay, so at time 0, the red car was at coordinates 0, 60, okay, and it's going south, sorry, 0, 4. I don't know why I wrote 60. It's at 0, 4, and it's going south at 60 miles per hour. Okay. Notice that the x-coordinate is not changing. It's just going south. The y-coordinate is changing. So from an original height of 4, I need to subtract 60 times t, because I'm going 60 miles an hour. So after 1 hour, I should be 60 miles south. I will be at negative 54. So similarly, what about the blue car? Okay, it starts at 3, 0. The y-coordinate is not changing, but the x-coordinate starts at 3 and goes down at a rate of 80 miles per hour. So this is x is equal to 3 minus 80t, and y is 0. This point here, x is 0, but y is 4 minus 60t. So at any point in time, my cars are at position 0, 4 minus 60t, and 3 minus 80t, comma, 0. So then I can ask, what's the distance between them? What is the smallest value that distance takes, and at what time? Okay, so now that we actually have some functions for where our cars are, if you couldn't answer it before, maybe now you can do the rest of this problem. Express the distance between the cars as a function of time and find when they're closest. Okay, so we've got fundamentally a right triangle going on where this length was 4 minus 60t, and this length was 3 minus 80t. So either by using the distance formula or just the Pythagorean theorem, the distance between the two cars is the square root of this enormous expression. Okay, this is a little complicated to try to work with by hand, but that's okay. We're allowed to use graphing calculators or computer software to help us find the minimum value of this distance. So if I graph it, it looks like this. Okay, the function they didn't even put on the slide. The function d is this mess, which is too complicated to work with by hand, so we're just going to let the computer graph it and assume that was correct. Okay, using the minimum value function of a computer or a calculator, we'll find out that this at about 0.05, the cars are closest and their distance is 1.4 miles. Now, 0.05 is about 1/20th, and remember, time was being measured in hours, and a 20th of an hour is about 3 minutes. So at about a time of 3 minutes is when they're closest, but they're still 1.4 miles apart. Okay, if you wanted to do the exact conversion to minutes, I mean, there it is. Whoops, sorry, my pen slipped. At 2.88 minutes. But honestly, just rounding this off to 0.05, we can see pretty quickly it's at about 3 minutes. Okay, so there's a couple examples. We kind of ramped up in difficulty, but also in believability as a practical application. The first example was just a geometry problem, points on a line and measuring distance. And it was pretty tractable, but it also didn't seem to have any real-world application. But by the end, we were dealing with distance of points moving through space, and it was more complicated. We kind of needed a computer to find that minimum point. But hopefully you believed that real-world applications are now getting closer to being within our grasp.